My name is Michael Pendazes, and this is Math 231 Linear Algebra. This is online lesson number 9. We're going to be covering Chapter 5. So the goal of this lesson will be to cover 5.1, Eigenvalues and Eigenvectors, 5.2, Diagonalization, and 5.3, Complex Vector Spaces. Okay, so let's get started. So definition 1. Okay. If A is n by n, then a non-zero vector x in Rn is called an eigenvector of A or of T sub A if AX is a scalar multiple of X that is AX equals lambda X for some scalar lambda. Lambda is an eigenvalue of A or of T sub A, and X is an eigenvector corresponding to A. Corresponding to lambda. Okay, so definition 1. If A is an n by n matrix, then a non-zero vector x in Rn is called an eigenvector of A or of T sub A if AX is a scalar multiple of x. That is, AX equals lambda x for some scalar lambda. Lambda is an eigenvalue of A or of T sub A, and x is an eigenvector corresponding to lambda. And so this is definition 1. It's the definition of an eigenvector of a matrix A and of an eigenvector corresponding to lambda. Okay? Okay, so this is the definition of eigenvector. So an eigenvector x of a matrix A is a vector x such that AX equals lambda x for some scalar lambda. Okay? Okay, so that's definition 1. We'll keep going. Example 1. Okay, x equals 1, 2 is an eigenvector of A equals 3, 0, negative 1, corresponding to n equals 3, since AX equals 3, 0, 8, negative 1, 1, 2 is equal to 3, 6, which is 3x. Okay, so that x is an eigenvector of that matrix A corresponding to lambda equals 3, since AX is equal to 3 times that vector x. Okay, so AX is equal to 3 times x, and so lambda is 3. Okay, so x is an eigenvector of the matrix A, and it's an eigenvector corresponding, it's an eigenvector of A corresponding to lambda equals 3. Because the value of lambda there, which is 3. Okay? Okay, Theorem 5.1.1. If A is n by n. Then lambda is an eigenvector. That lambda is an eigenvalue of A if and only if it satisfies the equation determinant of lambda I minus A is equal to 0. This is the characteristic equation. Of A. Okay, so if the matrix A is an n by n matrix, then lambda is an eigenvalue of A if and only if it satisfies the equation determinant of lambda I minus A equals 0. This is the characteristic equation of A. Okay, so this theorem is saying that this statement that lambda is an eigenvalue of A is equivalent to the statement that lambda satisfies that equation. Okay, and so this equation is called the characteristic equation of A. Okay, so the determinant of lambda I minus A equals 0 is equivalent to the equation lambda minus A sub 1 1 negative A sub 1 2 dot 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 negative A sub 1 n negative A sub 2 1 lambda minus A sub 2 2 dot 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 negative A sub 2 n dot 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 negative A sub n 1 negative A sub n 2 dot 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 lambda minus A sub n n. So the determinant of that equaling to 0. Okay. Okay, so if you find lambda I minus A, the matrix lambda I minus A, you take the determinant of that matrix and you set it equal to 0. And what you get when you calculate this determinant, you'll get what's called the characteristic polynomial, and it will be equal to 0. And that equation, the characteristic polynomial determinant of that matrix equaling to 0, that's called the characteristic equation of A. Okay? Okay. Okay. So in example 1 continued. Okay, so previously in example 1, we found that x equals 1, 2 was an eigenvector of this matrix A, corresponding to lambda equals 3, and so I showed that for you why that's the case. Okay, now if you take the determinant of lambda I minus A, what you get is the determinant of lambda times I, which is lambda times the 2 by 2 identity matrix, minus A, which is that matrix. Okay, so you take the determinant of lambda I minus A, and that's equal to, after you do this arithmetic, you get the determinant of the matrix lambda minus 3, 0, negative 8, lambda plus 1. Okay, and so when you do lambda times this minus that, you get this, and it's the determinant of that matrix. Lambda minus 3, 0, negative 8, lambda plus 1. And so the determinant of that matrix is, well, you just this times this, minus that times that. That's the determinant of a 2 by 2 matrix, and you get lambda minus 3 times lambda plus 1. And then that's minus 0 times negative 8. That's equal to lambda minus 3 times lambda plus 1. And, right, we know that the determinant of lambda I minus A equals 0. That's the characteristic equation, right? So this is our characteristic equation. And so we know, therefore, that the eigenvalues of A are lambda equals 3 and lambda equals -1. Those are the two values of lambda that make this product 0, right? If the product of two real numbers is 0, that means one or the other must be 0. So either lambda minus 3 is 0, which means lambda is 3, or lambda plus 1 is 0, which means lambda is -1. And so those are the two possible values of lambda that make the characteristic equation true. Okay, so those are the eigenvalues of matrix. Those are the eigenvalues of matrix A. Okay, and as a side note to this problem, when you expand, when the determinant of lambda I minus A is expanded in the characteristic polynomial equation, then what we get is that lambda to the n plus c1 lambda to the n minus 1 plus c2 lambda to the n minus 2 plus dot 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 plus c sub n is equal to 0. And this left side is called the characteristic polynomial of A. Okay, so that left side is called the characteristic polynomial of A. Okay, and this equation is numbered as 3 in section 5.1. Okay, and so what we see here is how to find the eigenvalues of a matrix A. You take the determinant of lambda I minus A and you set equal to 0, and you solve for the values of lambda that make the equation true. You factor out the characteristic polynomial, and you find the values of lambda that will make the polynomial equal to 0. One of its factors has to be 0. Okay? Okay, so that is the beginning of 5.1. Now let's keep going. Okay, we're learning about eigenvectors and eigenvalues. So the next theorem is Theorem 5.1.2. And that theorem is if A is n by n triangular, right? A triangular matrix is an upper triangular matrix, a lower triangular matrix, or a diagonal matrix. So if A is n by n triangular, then the eigenvalues of A are the entries on the main diagonal. Okay, so if A is n by n triangular matrix, then the eigenvalues of A are the entries on the main diagonal of A. Okay, so as an example of that, let's say you have the matrix A, which is the matrix 1, 0, 0, 0, 5, 0, 0, 0, -1. This is a diagonal matrix, which is also a triangular matrix. And as a triangular matrix, that means that the eigenvalues of A are 1, 5, and -1. Okay? It's just the entries on the main diagonal of A. Okay? And if an entry is repeated, it just means you don't have a new, you just don't have as many eigenvalues as rows. Okay. Okay, so the next is Theorem 5.1.3, and that theorem says if A is n by n, the following are equivalents. Lambda is an eigenvalue of A. B. Lambda is a solution to the determinant of lambda I minus A is equal to 0. C. Lambda I minus A x equals 0 has non-trivial solutions. Okay, so lambda I minus a times x equals 0 has non-trivial solutions, and D, there is a non-zero vector x such that ax equals lambda x. So this is Theorem 5.1.3. It says if A is an n by n matrix, the following are equivalent. So these are our four statements, and it's saying these four statements are equivalent, have the same truth value. A, lambda is an eigenvalue of A. B, lambda is a solution to the determinant of lambda I minus a equals 0. C, lambda I minus a times x equals 0 has non-trivial solutions. D, there is a non-zero vector x such that ax equals lambda x. Okay, and so those four statements are equivalent. A is from the definition of an eigenvalue, to understand what that means. Okay, lambda solves the equation. Saying this equation has non-trivial solutions means that there's a vector x that's not the zero vector where this equation holds. Okay, that means that the solutions are values of x, and so saying this equation has non-trivial solutions means that there's a non-zero x that satisfies that equation for a fixed value of lambda. Okay, so again, this equation, what C is saying is that this equation has a solution for x that's not the zero vector, so where you're considering an eigenvalue, a fixed value of lambda, which is an eigenvalue of A. Okay, and D just says there is a non-zero vector x such that A times x equals lambda x, and lambda here is a fixed value of lambda. Lambda is the eigenvalue that you're thinking of all four statements. And so you're taking that fixed lambda, whatever it is, and you're saying that there's a non-zero vector x such that ax equals that number that you fixed times that same vector x. Okay? And so that is Theorem 5.1.3. So you have to read that and spend some time studying that theorem. Okay, so the eigenspace of A corresponding to lambda can be viewed as one thing, which is the non-zero vectors that satisfy lambda I minus a x equals 0. The next thing, that the null space as the null space of lambda I minus a. The next thing is the kernel of t sub lambda I minus a, which is a function from n space to n space. Okay, and then 3, the set of vectors x such that ax equals lambda x. Okay, so the eigenspace of A corresponding to lambda can be viewed as these four things. The non-zero vectors that satisfy lambda I minus a times x equals 0, and the vectors referring to are the x vectors. The null space of lambda I minus a. Okay, the null space of lambda I minus a, that just means the null space of a matrix is just, for instance, the null space of A would be the solutions to AX equals 0, right? So the null space of a matrix A is the solutions to AX equals 0. So the null space of lambda I minus a is the solutions to lambda I minus a times x equals 0. That's what A says. Well, that's what the first thing says, 0.0. it's the non-zero vectors x such that this equation holds. Right? So saying the null space of lambda I minus a is exactly the same as saying the vectors x that satisfy lambda I minus a times x equals 0. Okay? The kernel of this matrix transformation. Now the kernel of a matrix transformation is the set of all vectors that the transformation maps to 0. Well, t sub lambda I minus a is left multiplication by a vector. T sub lambda I minus a of x is left multiplication by lambda I minus a of vector x. So t sub lambda I minus a x of x is equal to left multiplication of lambda I minus a. And the kernel of this matrix transformation is just a set of vectors that this transformation maps to 0. And so that would just mean it would be the set of all x such that lambda I minus ax is equal to 0. That's exactly the same as this, okay? And so the set of all vectors in Rn that this matrix transformation maps to 0 means just the set of all vectors x such that lambda I minus a times x is 0. Same thing, okay? And the set of all vectors x such that ax equals lambda x, well, if ax equals lambda x, it's equivalent to saying ax minus lambda x equals 0. And that's equivalent to saying that a minus I lambda x equals 0. And that's equivalent to saying lambda I minus, just taking the negative on both sides, lambda I minus a x is equal to 0. So saying this, finding the solutions to ax equals lambda x is the same as finding the solutions to lambda I minus a times x equals 0. And so that statement is also the same. And so the eigenspace of A corresponding to lambda can be viewed in these 4 ways. But they're all referring to the exact same set, the eigenspace of A corresponding to lambda. Okay? Okay. Okay, example 6. Find bases for the eigenspaces of A, which is equal to -1, 3, 2, 0. Okay? So find bases for the eigenspaces of that matrix A, which is -1, 3, 2, 0. Okay, and so solution. Okay, I want to find bases for the eigenspaces of that matrix. And so first I need to find the eigenvalues of that matrix, right? So step 1, find the eigenvalues of A. Okay, so step 1 is find the eigenvalues of A. And so the eigenvalues of A, right, are the values of lambda such that lambda I, the determinant lambda I minus A, is equal to 0. Right? Okay, and so we just need to solve the equation. And so that equation is equivalent to the equation lambda plus 1 minus 3 minus 2 lambda equals 0. So the determinant of lambda I minus A is that. And so I talked a little bit how to view that, find that determinant in another board earlier. And so, so now the determinant that is equal to 0, that's equivalent just saying lambda plus 1 times lambda minus -2 times -3 is equal to 0. And that's equivalent to saying lambda squared plus lambda minus 6 is equal to 0. Okay? And that's equivalent to saying lambda plus 3 times lambda minus 2 is equal to 0. Okay? And, right, because there's a 3 lambda minus 2 lambda is a 1 lambda, 3 times -2 is -6, lambda times lambda is lambda squared. Okay, so now that's equivalent to saying that lambda equals -3 or lambda equals 2. Those are the solutions. So the solutions are just those are solutions. Okay, -3 or 2. And so step 1, find the eigenvalues if A is accomplished. Lambda equals -3 or 2. Step 2 is find step 2 is find the bases for the eigenspaces corresponding to each eigenvalue separately. Okay, so each eigenvalue will involve its own process for finding bases for an eigenspace corresponding to that eigenvalue. So step 2 is find bases for the eigenspaces corresponding to each eigenvalue separately. So we're going to have to look at each eigenvalue separately. So let's do lambda equals 2 first. Okay, lambda equals 2, that's one of the eigenvalues. And so to find the eigenspace, what you need to do is you need to find lambda I minus A times x is equal to 0. You need to find the general solution to that equation. Find the general solution of that equation when lambda equals 2. Okay, so it's this equation, lambda I minus A times x equals 0. And then for each eigenvalue you choose, you plug that eigenvalue in there and you find the general solution to the linear system represented by that equation. So when lambda equals 2, you get 2i minus A times x equals 0. And what that matrix is, 2i minus A times x, is 3, -3, -2, 2 times x, which is x1, x2. It's equal to the 2 by 1, 0 matrix, right? So 2i minus A is this matrix, x is this matrix, 0 is that matrix. So 2 minus -1 is 3, 0 minus 3 is -3, 0 minus 2 is -2, 2 minus 0 is 2. Good. Okay, so we get that. And so you just need to find the solutions for those from that equation. And so I'm going to multiply the first row by 1/3. So I'm going to find, I'm going to get this to reduced echelon form. Find the general solution. And what I'm going to get is 1, -1, 0 here. Multiply this, then 2 times this plus that. Get that. And so then that means that if x2, this is the leading one here, so x2 is a parameter, and x1 is equal to t also. So the solutions, the general solution to this the general solution to this equation, the general solution to that equation is x1, x2 is equal to t, which is t times 1, 1. And so the set of all vectors of this form, for t takes any real number, that's the general solution when lambda equals 2. Okay? Okay, so that's there. So that's t1, 1. So when lambda equals 2, the general solution of 2i minus A times x equals 0 is x is equal to t1, 1, such that t is a real number. Okay? That's the general solution, any multiple of the vector 1, 1. So that's the, okay, so then that's the general solution. And the basis for this eigenspace is, for this eigenspace is just the individual vector 1, 1. It spans the vector space, and it's a non-zero vector, and so the set containing only that is linearly independent. This is a basis for this eigenspace corresponding to lambda equals 2. Okay, that's the basis for the eigenspace corresponding to lambda equals 2. Now, if lambda equals -3, you want to find the general solution of lambda I minus a times x equals 0 when lambda equals -3. Okay, so we want to find the general solution of lambda I minus a times x equals 0 when lambda equals -3. And so that's -3i minus a times x is equal to 0 is equivalent to -2 -3 -2 -3 times x is equal to 0. Okay, so lambda I minus a is this matrix. -3 minus -1 is -2. 0 minus 3 is -3. 0 minus 2 is -2. Minus 3 minus 0 is -3. So, okay, we want to find the general solutions. To find all solutions, all these vectors that satisfy the equation. And so, if we look at the linear system here, using an augmented matrix, we can just multiply that by -1/2. We get that's 3/2 here. That's 3/2. And if I were to take -1 times this row and add to that one, it would just cancel. And so that means that x2 is our parameter, right? Because our leading one is here, that corresponds with x1. x2 is a parameter. x1 then is -3/2 t. And so the general solution to x, which is x1, x2, is the vector -3/2 t and t. And that's the same as t times -3/2 1. Okay, and so a basis for this eigenspace is just -3/2 1. And so the basis for this thing is the vector -3/2 1. Okay, that's a basis for the eigenspace corresponding to lambda equals -3. This is a basis for the eigenspace corresponding to lambda equals 2. So first you find the eigenvalues of your matrix, and then for each eigenvalue you find the basis for the eigenspace corresponding to that eigenvalue. Okay? Right? And to find the basis for the eigenspace corresponding to an eigenvalue, you have lambda I minus a times x equals 0. You plug in each eigenvalue one at a time. For each eigenvalue you plug that in, you keep that eigenvalue, you find a general solution to that linear system, and then you find a basis for that general solution, which is just the vectors used in your general solution, and then that makes up a basis for that eigenspace, for that eigenvalue. Okay, you do it for each one. And so now we're done with example 6. Okay. Okay, so Theorem 5.1.4. A square matrix A. I'm just gonna write a square matrix capital A is invertible if and only if lambda equals 0 is not an eigenvalue of A. Okay? So when you have a square matrix A, saying it's invertible is equivalent to saying that lambda equals 0 is not an eigenvalue of A. So if you have a square matrix A and 0 is an eigenvalue of A, then it's not invertible. Okay? Theorem 5.1. That was Theorem 5.14. That was Theorem 5.14. This is Theorem 5.15. And so this is the equivalent statements theorem again, which is all those statements that are equivalent. Equivalent statements theorem. Okay. And so what we're going to do is add this one to Theorem 5.1.4. And so it's U, statement U, which is lambda equals 0, is not an eigenvalue of A. And so we had that long list that started with the term A is non-zero and had a bunch of other statements. One of them was the term A is not equal to 0. And so just a long list of statements. And you add this to the list that lambda equals 0 is not an eigenvalue of A. Okay? And then definition 2 to this section is if T from V to V is a linear operator on a vector space on a vector space V, then a non-zero vector X then is non-zero vector X in V is an eigenvector of T if T of X is a scalar multiple of X, or T of X is equal to lambda X for some lambda, for some scalar lambda. Lambda is an eigenvalue of T, and X is an eigenvector corresponding to lambda. Okay, so if T from V to V is a linear operator on a vector space V, then a non-zero vector X in V is an eigenvector of T if T of X is a scalar multiple of X, or T of X equals lambda X for some scalar lambda. Lambda is an eigenvalue of T, and T is an eigenvector corresponding to lambda. Okay, so this is the definition of an eigenvalue of a linear operator T, and the eigenvector and the definition of an eigenvector corresponding to lambda when talking about linear operators. Okay. Okay. Going. Okay, so the eigenspace of T corresponding to lambda is the kernel of T sub lambda I minus A, or the subspace of V such that T of X is equal to lambda X. Okay, so the eigenspace of T corresponding to lambda is the kernel of T sub lambda I minus A, or the subspace of V such that T of X is equal to lambda X. Okay? The kernel of t sub lambda I minus a, that's just the vectors. Right, t sub lambda I minus a is just left multiplication by lambda I minus a of a vector x. Right? So t sub lambda I minus a, that's t sub lambda I minus a. And the kernel of that matrix transformation are just all the vectors x such that t sub lambda minus a of x is equal to 0. Okay? But now if you say t of x is equal to lambda x, that's the same as saying ax is equal to lambda x, because t of x is left multiplication by a, and that's just equivalent to lambda I minus a times x is equal to 0. So the set of x values such that t of x equals lambda x is the same as the set of x values such that ax equals lambda x. That's the same as the set of x values such that lambda I minus a times x equals 0. Okay, and this is the kernel. This is the kernel of t sub lambda I minus a. Right, so x. So that's good. The kernel of t sub lambda I minus a is the set of all vectors x such that lambda I minus a times x equals 0. That's the set of all x such that ax equals lambda x. That's the set of all x such that t of x equals lambda x. Okay, and all these x's lie within our vector space V. Okay, and the set of solutions is a subspace of V. And so, okay, so the subspace of V, that the kernel of t sub lambda I minus a is the subspace of V, and it's the same as the subspace of V, which is the solutions to this equation, t of x equals lambda x. That's what I'm saying here at the top. Okay, t of x is left multiplication by a, and t sub lambda I minus a is left multiplication by lambda I minus a. Right? And the kernel of a matrix transformation is just the set of all vectors x such that left multiplication by that thing in the subscript is 0. Right? So the kernel, for instance, the kernel of t sub a is the set of all vectors x such that ax equals 0. The kernel of t sub a is the set of all vectors x such that ax equals 0, because t sub a is left multiplication by a. And so the kernel of a matrix transformation is all the things that get sent to 0. And so the kernel t sub a is just what vectors, when you multiply on the left by a, give you 0. That's ax equals 0. Okay, so the kernel t sub a is all the solutions to ax equals 0. And so the kernel t sub lambda I minus a is all the solutions to lambda I minus a times x equals 0. And you just do some algebra, that's ax equals lambda x, and t of x is left multiplication by a, so that's ax. Okay? Okay. So that's the end of 5.1. Okay, 5.2, diagonalization. Okay, so given that A and P are n by n matrices and P is invertible, then if you have a transformation that takes the matrix A to P inverse AP, this is called a similarity transformation. Okay, so a lot of properties of the matrix A are preserved by this similarity transformation. Okay, so when you take the matrix A and you take the map, the function, the similarity transformation that goes from A to P inverse AP, again, qualities about this matrix will be the same for that matrix. Okay, and so for instance, let's see this example of what I mean. Let's say we take the matrix B to equal P inverse AP. Then the determinant of B is equal to the determinant of A, since the determinant of B is equal to the determinant of P inverse AP. But the determinant of a product of matrices is just a product of their determinants. And this is the determinant of P inverse times the determinant of A times determinant of P. Okay? Well, the determinant of P inverse is 1 over the determinant of P. So this is 1 over the determinant of P times determinant of A times determinant of P. And so 1 over determinant of P times determinant of P cancel, and you get that equals to the determinant of A. So the determinant of B is equal to the determinant of A. So the determinant of P inverse AP is the same as the determinant of A. And don't forget, we're assuming that P is invertible. Okay? That's why I could write P inverse here. If P was not invertible in this step, I could not have talked about a matrix P inverse there. It wouldn't exist, right? P being invertible means there exists a matrix transformation P inverse. And so this is required in order to have this relationship. Okay, and so one of the things that are preserved under the similarity transformation is the determinant. And so if you take a matrix A and you transform it to P inverse AP, the determinant stays the same. Okay, as shown here. Okay, so now I'm going to draw as a table, and I'm going to list some of the things that are preserved under this similarity transformation. Things that stay the same. Okay. Before and after transformation. And so in the book, this is table 1, which is called similarity invariance. Property. Property description. Determinant. The determinant A and P inverse AP have the same determinant. Okay, so A and P inverse AP have the same determinant. So first property is determinant, and like I showed in the last board, A and P inverse AP have the same determinant. And so that's a similarity invariant. Invertibility. Okay. A is invertible if and only if P inverse AP is invertible. Okay? So the second property that's preserved under the similarity transformation is invertibility. The next one is rank. A and P inverse AP have the same rank. Remember, the rank is the dimension of the row space of the matrix. Okay? The row space of the matrix is the span of the rows of the matrix. It's a vector space, and so it has a dimension, and the dimension of that vector space is the rank of that matrix. Okay? So the rank of A and P inverse AP are the same. Okay? The next thing is nullity. A and P inverse AP have the same nullity. So you're seeing where this is going. A and P inverse AP have the same nullity. Okay, so the nullity is the dimension of the null space of a matrix. So the null space of A is the set of all solutions to AX equals 0. Right? Solutions to AX equals 0, the vector is X there. The solutions to AX equals 0 is the null space of A, and it has a dimension as a vector space. The dimension of the solution space to AX equals 0 is the null space of a matrix A. And so the nullity is the dimension of that vector space, of the null space. And so the nullity of A and P inverse AP are the same. The next one is trace. Okay? A and P inverse AP have the same trace. Right? Trace is the sum of the values on the main diagonal of a matrix. Right? So if you have a matrix, you have the main diagonal, the entries on the diagonal of the matrix. Add up those entries, that's a trace of a matrix, right? And so the trace of A and P inverse AP are the same. Okay, characteristic polynomial. So characteristic polynomial, so A and P inverse AP have the same characteristic polynomial. Okay, so A and P inverse AP have the same characteristic polynomial. Okay, right, so the characteristic polynomial, right, are the solutions to the determinant of lambda I minus A is equal to 0. The solution, the values of lambda such that the determinant of lambda I minus A is equal to 0. So the characteristic polynomial of A and P inverse AP are the same. Okay, so the solutions to the equation lambda I minus A times x is equal to 0, the set of all x values that satisfy that equation is the same as the set of solutions to lambda I minus P inverse AP times x equals 0. And so the set of all vectors x such that lambda I minus A times x equals 0 is the same as the set of all vectors x such that lambda I minus P inverse AP times x is equal to 0. That's what it means for the characteristic polynomials to be the same. Oh, no, sorry. Well, no, sorry. Oops. I mean, what I mean is that it's saying the determinant of lambda I minus A is equal to 0. The solutions lambda to that equation, this is an equation, and lambda, there's values of lambda. The values of lambda that satisfy the equation are the same as the values of lambda that satisfy this equation, lambda I minus P inverse AP is equal to 0. That's what I mean. Okay, so values of lambda that satisfy that equation are the same as the values of lambda that satisfy this equation. That's what it means for the characteristic polynomials of A and P inverse AP to be the same. Okay, next one. Eigenvalues. Okay, so A and P inverse AP have the same eigenvalues. Okay, so the eigenvalues of a matrix are just the all the values of lambda such that the determinant of so the eigenvalues are just the values of lambda such that lambda I minus A, the term of lambda I minus A equals 0 is the eigenvalues, right? That's the same as the values of lambda such that the term of lambda I minus P inverse AP is equal to 0. Right? All the solutions for lambda here and here, they're the same. That's what same eigenvalues mean. When I said the same characteristic polynomial, now I can figure. Okay, so this is for eigenvalues, and then for characteristic polynomial. So I'm going to go back 1 second. For characteristic polynomial, it means that lambda I minus A the determinant of lambda I minus A is equal to the determinant of lambda I minus P inverse AP. Okay, that determinant is the characteristic polynomial. So that's the characteristic polynomial of A, that's the characteristic polynomial of P inverse AP, and they're the same. That's what it means for the characteristic, this part. Okay. Okay. And then Eigenspace Dimension. Okay, so if lambda is an eigenvalue of A, and hence of P inverse AP, right? Because they have the same eigenvalue. So if lambda is an eigenvalue of either, then the eigenspace of A corresponding to lambda and the eigenspace of P inverse AP corresponding to lambda have the same dimension. Okay, so for eigenspace dimension, I'm talking about below that line. Okay, so if lambda is an eigenvalue of A and of P inverse AP, then the eigenspace of A corresponding to lambda and the eigenspace of P inverse AP corresponding to lambda have the same dimension. So for each eigenvalue, it has a corresponding eigenspace. Okay, and it's a vector space. So every eigenvalue has a corresponding eigenspace for both A and P inverse AP. And that eigenspace has a dimension. And so if you have an eigenvalue lambda of both A and P inverse AP, then that lambda will give you an eigenspace for A corresponding to lambda and an eigenspace for P inverse AP corresponding to lambda. So both A and P inverse AP will have an eigenspace corresponding to some fixed lambda. So what this is saying is that the dimensions of those two things are the same. The dimension of the eigenspace of A corresponding to lambda is the same as the dimension of the eigenspace of P inverse AP corresponding to lambda. That's what that last thing says. Okay, that's invariant under this transformation. The dimension of the eigenspace corresponding to any eigenvalue stays the same from A to P inverse AP. So if you start with the matrix A and you transform it under the similarity transformation to P inverse AP, if you take an eigenvalue of A and you take an eigenspace corresponding to that eigenvalue and you find its dimension, then when you go to P inverse AP and you take the same eigenvalue and take the eigenspace of P inverse AP corresponding to that eigenvalue, the dimension of that is the same as the dimension of the original eigenspace of A corresponding to that lambda. Okay, let's keep going. Okay, so So if A and B are square matrices, we're going to abbreviate as square. So if A and B are square as matrices, then B is similar to A if there's invertible P such that P is equal to B, such that B is equal to P inverse AP. Okay? So if A and B are square matrices, then B is similar to A if there is invertible P, matrix P, such that B equals P inverse AP. Okay? B being similar to A implies that A is similar to B. So we say A and B are similar. Instead of saying one matrix is similar to the other, we just say that the two are similar to each other. We just say A and B are similar. Okay? Instead of saying A is similar to B or B is similar to A, we'll just say A and B are similar because one implies the other. Okay? So definition 1 says if A and B are square matrices, then P is similar to A if there's an invertible matrix P such that B equals P inverse AP. That's the definition of B being similar to A. Okay, definition 2. A square matrix A, is diagonalizable if it is similar to some diagonal matrix capital D. And if that happens, we then say, in such a case, So so A is diagonalizable if it's similar to some diagonal matrix D. What that means is that A is equal to P inverse AP, where P is invertible. Okay? So a square matrix A is diagonalizable if we can express A as equal to P inverse AP, where that P in that equation is diagonalizable. And we say in such a case that A is equal to P inverse DP. It's A here is similar to D. Okay, or D is similar to A, but that's good. Okay, and so we say in such a case P diagonalizes A. Okay, so P diagonalizes A. Okay, in such a case, the matrix, invertible matrix P that we use in this equation is the matrix that diagonalizes A. Okay, so that's definition 2. It's definition of a diagonalizable square matrix. And so you have to be dealing with a square matrix A. Okay? If you have a matrix that's not square, it's automatically not diagonalizable. Okay, so Theorem 5.2.1. If A is n by n, the following are equivalent. Part A, capital A is diagonalizable. So capital A has n linearly independent eigenvectors. Okay, so if A is n by n, the following are equivalent. A is diagonalizable, and B, A has n linearly independent eigenvectors. Okay, so this theorem is saying that the following are equivalent. It's saying that this statement, A is diagonalizable, has the same truth value as A has n linearly independent eigenvectors. Okay, so statement A is diagonalizable, right? Remember, that means that there is a matrix, there's invertible. That means there exists an invertible matrix P such that A equals P inverse dP, where D is a diagonal matrix. There's some diagonal matrix D such that, and some invertible matrix P such that A equals P inverse dP. That's what it means for A to be diagonalizable. Okay. Okay, and then B, A has n linearly independent eigenvectors. Well, right? The eigenvectors of A are just vectors x such that AX equals lambda x for some scalar lambda. Those are the eigenvectors, right? And so this statement is saying that you can find n choices for x where they form a linearly independent set. Okay? So there's such a way to choose n vectors x here that satisfy this equation, where each one can have its own value of lambda. They can have the same or different values of lambda. But you can choose n vectors x such that each one has its own or possibly the same as another one value of lambda such that this equation would hold. And for those n vectors x, they form a linearly independent set. That's what statement B says. And so this theorem is saying that these two statements have the same truth value. They're both true or they're both false, given that A is an n by n matrix. Okay? Okay. Theorem 5.2.2. A, if lambda 1 to lambda sub k are distinct eigenvalues, So if lambda 1 to lambda k are distinct eigenvalues of A, and if v1 to vk are corresponding eigenvectors, then v1, the set containing those vectors v1 to vk, is linearly independent. So this tells us how we could use Theorem 5.2.1. So that's helping us here with that previous theorem. Okay. So if lambda 1 to lambda k are distinct eigenvalues of A, and if v1 to vk are corresponding eigenvectors, meaning lambda 1 is an eigenvalue of A, and for that eigenvalue has corresponding eigenspace. That corresponding eigenspace is made up of what's called eigenvectors, and so v1 is one of the vectors in the eigenspace corresponding to lambda 1. v2 is one of the vectors in the eigenspace corresponding to lambda 2. v3 is an eigenvector in the eigenspace corresponding to lambda 3, up to including the last one, the kth one, where v sub k is an eigenvector in the eigenspace corresponding to lambda sub k. Okay, so these are all the eigenvalues of a matrix A. Each one has its own eigenspace, and you're taking one vector from each of those eigenspaces. And so you're getting the vectors v1 to vk. Okay, so if you do that, then the set of those k vectors, v1 to vk, is linearly independent. Okay? Now, if you had n distinct eigenvalues of a matrix A, right? So A is an n by n matrix, n rows and n columns. And so if you had a matrix A with n rows and n columns, and you had it, and if it turned out you don't have to have it this way, but if it turns out that there are n distinct eigenvalues for that n by n matrix A, those n distinct eigenvalues, well, then you could choose any vector in each of those eigenspaces. Then what has to happen is that you'll end up with n vectors that form a linearly independent set. And this says that if you have n linearly independent eigenvectors, that would be true. And then you could say your matrix A is diagonalizable. Okay? So as soon as you get n distinct eigenvalues of a matrix for an n by n matrix A, once you get n distinct eigenvalues, that means that your A is diagonalizable from part A of this theorem. You would then have to get n vectors that form a linearly independent set, and those n vectors are eigenvectors of your matrix A. B would be true, which means by this theorem A would also be true, has the same truth value of B, and then A would be diagonalizable. Okay, so that's important to know. B. This is exactly what I'm going to say. An n by n matrix with n distinct eigenvalues is diagonalizable. So with the previous theorem and part A, B is deduced from that. And so you wouldn't have to write B down. Well, I guess you would write down to say it, but you could deduce this just, not obviously, but not too difficultly from this theorem and A. So not too difficultly. So an n by n matrix with n distinct eigenvalues is diagonalizable. Okay, so an n by n matrix with n distinct eigenvalues is diagonalizable by the reasons I just mentioned already. So I proved B with A and Theorem 5.2.1. Okay. Okay, so you have these two theorems now in addition to everything else, right? So again, even though this is a lot of material, the more theorems and the more definitions you have, the easier it is to get results, because the more you know, the easier it is to derive something if you already know all this stuff about the subject, right? Okay, so next thing. for sorry. A procedure for diagonalizing an n by n matrix. So a procedure for diagonalizing an n by n matrix. So step one is find a basis for each eigenspace. And count the total number of vectors. Okay, so you could still get n linearly independent eigenvectors even if you do not have a total of n distinct eigenvalues. Okay, each eigenvalue has an eigenspace. And that eigenspace has a dimension. And if that dimension is bigger than 1, you may get more than one linearly independent eigenvector from just one eigenvalue. So it doesn't have to be the case that you have to get your linearly independent eigenvectors each from a different eigenvalue. You could have one eigenvalue of dimension 10, and you could get 8 linearly independent eigenvectors for that dimension 10 eigenspace corresponding to one value of lambda, if that makes any sense. So you can get more than one linearly independent eigenvector from just one eigenvalue. Okay, so in step 1, we have to do this step. When we want to find a basis for each eigenspace for a matrix. Okay, we want to find a basis for each eigenspace and count the total number of vectors. And so if I get 2 eigenspaces, and I find bases for each of those eigenspaces, and if in the first basis I find 3 linearly independent eigenvectors, and for the other eigenspace I find 2 linearly independent eigenvectors, then counting the total, I would have a total of 5 linearly independent eigenvectors for 2 eigenspaces and 2 values of lambda. Okay, so you have to count the total number of eigenvectors, linearly independent eigenvectors. Okay, so that's step 1. Step 2. Continuing step 1. If you found n, and what is n? N is it's an n by n matrix we're talking about in the beginning. And so n is the number of rows or columns, which is the same of that matrix. And so if you found n, if you counted the total number of eigenvectors you use for the bases, okay? So when you find bases for each eigenspace, the vectors in those bases form linearly independent sets, okay? So if you found a total of n vectors from the bases from step 1, if you found a total of n, then the matrix is diagonalizable. The original n by n matrix. If not, if you did not find n, you found less than n, you can't find more than n. So if you found less than n, then the matrix is not diagonalizable. If you find more than n, that means you did something wrong. Okay, you did something wrong with your math, and that you should not get more than n. So you can only get n or less than n. Okay, so if you don't find n, if you find less than n, then the matrix is not diagonalizable. And so in this procedure for diagonalizing an n by n matrix, if you do not find n, if you count the total number of vectors here and you don't get n, you get less than n, then you stop right there because you cannot diagonalize the matrix. Okay? But if you find n, then you continue to step 2. Okay, and step 2 says, if the matrix is diagonalizable, only if it is, so if the matrix is diagonalizable, then form the matrix P, where the columns of P are the basis vectors that you found for each eigenspace. Okay, so form this matrix P. These are the columns of P, P1 to Pn, whose column vectors are the same as the n basis vectors So then in step 2, if the matrix is diagonalizable, then form that P, where the column vectors are the same as the n basis vectors in step 1. And then 3, okay, and then step 3 is that P inverse AP is a diagonal matrix whose successive diagonal entries are the eigenvalues lambda 1 to lambda n that correspond to P1 to Pn. Okay, so P inverse AP is a diagonal matrix whose successive diagonal entries are the eigenvalues lambda 1 to lambda n that correspond to P1 to Pn. Okay, so if you have a matrix A whose eigenvalues are lambda 1 to lambda n. Now I said that you may not have n distinct eigenvalues, and so lambda 1 to lambda n does not mean n different numbers. You may have, if it is diagonalizable, then you'll have n eigenvalues, and some of those eigenvalues will be repeated. So for instance, if you have a 3 by 3 matrix A, and you only have eigenvalues 1 and 2, you may have 1, 1, 2 as your eigenvalues, or you may have 1, 2, 2, but it will depend on what happens in the problem. It will depend on the dimensions of the eigenspaces for each eigenvalue. Okay, so if lambda equals 1 had dimension 2 and lambda equals 2 is dimension 1, then you'd have 2 eigenvalues of 1 and 1 eigenvalue of 2. So the number of times you repeat an eigenvalue depends on the exact dimension of the eigenspace corresponding to the eigenvalue. So if you had, again, if you have lambda equals 1 and has dimension 3, then lambda equals 1 you'd repeat 3 times. Okay? And so you repeat in that way. P inverse AP is a diagonal matrix where the diagonal entries are the n eigenvalues that can be repeated. Lambda 1 to lambda n, those are the entries on the diagonal. And the order on the diagonal of lambda 1 to lambda n will correspond with the order that you chose when you formed the matrix P. And so when you made the matrix P, you had n vectors in step 1. And I makes no specification on the order of those P's. And that's fine. You can order the n vectors in step 1, P1 to Pn in any order. But when you choose an order, when you put them in any order, that order will determine the order of the eigenvalues that go in the diagonal of P inverse AP. Okay? So when you form that matrix P, the order you choose for the n vectors from step 1, that order will then determine what P inverse AP is, and that order will determine the order of the eigenvalues on the diagonal. And that matrix, whose diagonal entries are the eigenvalues lambda 1 to lambda n, and everywhere else is 0, that will be P inverse AP. Okay? Okay, so this is a procedure for diagonalizing an n by n matrix. The last step would be, with that P, you get P inverse AP, and you would get the diagonal matrix with those eigenvalues on the main diagonal, in the order that you chose from the order of the P's in the column vectors that form the matrix P. Okay, so those are the 3 steps, and so what you need to do is you just need to do these 3 steps. You need to take a matrix A, and you need to know how to follow each of these 3 steps, and you do it in this order, and then you're done. Okay? So early in the lesson, I showed you how to do step 1. Step 2, you just take those vectors and make them the column vectors of P. And then step 3, the eigenvalues corresponding to those P in that order will be the entries on the main diagonal for P inverse AP. Okay, so most of the work is just step one. Okay. Example 1. Example 1. Find P that diagonalizes this matrix A. That diagonalizes that matrix A, where this matrix A is 0, 0, negative 2, 1, 2, 1, 1, 0, 3. Okay, so find P that diagonalizes that matrix A. So let's do that. So the solution is we're going to find the characteristic polynomial, and so to find the characteristic polynomial is determinant of lambda I minus A is equal to 0. You want to find all values of lambda that satisfy that equation. And so the values of lambda, so when you take that, that's equivalent to lambda minus 1 times lambda minus 2 squared is equal to 0. Okay, so the determinant of lambda I minus A is lambda minus 1 times lambda minus 2 squared, and it equals 0. Okay, and so the values of lambda that satisfy that equation are lambda equals 1 and lambda equals 2. So those are the two eigenvalues of that matrix A. Okay, for lambda equals 2, what you get is that the two, a basis for that eigenspace is negative 1, 0, 1, and P2, which is 0, 1, 0. So these are two basis vectors that form basis for the eigenspace corresponding to lambda equals 2. And for lambda equals 1, you get one basis vector. You get one vector that forms a basis for the eigenspace corresponding to lambda equals 1. It's negative 2, 1, 1. Okay. So again, so you have determinant lambda I minus A equals 0. You get the characteristic, the determinant of that is the characteristic polynomial lambda minus 1 times lambda minus 2 squared. You say equals 0. That's the characteristic equation. The values that satisfy that equation for lambda are the eigenvalues of A. That's lambda equals 1 and lambda equals 2. P1 and P2 here form a basis for the eigenspace corresponding to lambda equals 2. P3 forms a basis for the eigenspace corresponding to lambda equals 1. And so now, that's step 1. So step 1 is done. We're done with step 1. Find a basis for each eigenspace. And we count the total number of vectors. We have 3, and n is 3 in this problem. There's 3 rows and 3 columns of A. It's a square matrix with 3 rows and 3 columns. And so we have 3 basis vectors in total. And so step 1, then step 2 says if you have n, which we do, many basis vectors, eigenvectors, basis vectors, then we can continue and form the matrix P, and the columns of matrix P are formed by those P's there. So P1, P2, P3 are the columns of P, and so that's negative 1, 0, 1, 0, 1, 0, negative 2, 1, 1. So that's P. And so that matrix P now is, that's step 2. And so that matrix P is the matrix that diagonalizes A. Okay? And so P here diagonalizes A. So that P diagonalizes A. Now find the P that diagonalizes A. We just did. It's that. Okay? That's the answer. Okay? We could have chosen any order for the P's here. If I change the order, I could just get another vector, another matrix that diagonalizes A. There's more than one. Okay? In this case, there's 6. Well, sorry, there's actually infinitely many. Okay, but there's infinitely many. But if I started with these 3, there's 6 ways to order these 3 vectors. And so there's 6 ways I could order P1, P2, and P3. But there's infinitely many bases I could have chosen for either vector space. And so there's infinitely many choices for P3 here, and there's infinitely many choices for P1 and P2 there. So technically there's actually infinitely many matrices P that diagonalize this matrix A in this example. Okay, but anyway, we're continuing. Okay, no, a triangular matrix with distinct entries on the main diagonal is diagonalizable with eigenvalues. So a triangular matrix with distinct entries on the main diagonal is diagonalizable with eigenvalues, those entries on the main diagonal. So I mentioned that already before. Those entries on the main diagonal. Okay, right? If you have n distinct eigenvalues, then each of those eigenvalues will have an eigenvector, and so you'll have n linearly independent eigenvectors, which means your matrix is diagonalizable. Okay. Okay. But it also goes further. It says that the eigenvalues are the entries on the main diagonal. Okay. So then theorem 5.2.3. If k is an integer, lambda is an eigenvalue of a, and x a corresponding eigenvector to that eigenvalue a, then lambda raised to the kth power is an eigenvalue of a to the k. So if you thought stuff before was hard, now we're raising things to the kth power. So, and x is a corresponding eigenvector. Okay, so k is an integer. So if k is an integer and lambda is an eigenvalue of a, and x is a corresponding eigenvector to the eigenspace. So lambda is an eigenvalue of a, right? There's an eigenspace corresponding to that lambda value, and x is an eigenvector in that eigenspace. Then lambda to the k is an eigenvalue of a to k, and x is a corresponding eigenvector. Okay? Okay, so if lambda is an eigenvalue of a, right, then if you're thinking of the matrix a to the k, then correspondingly lambda to the k is an eigenvalue of a to the k. But if lambda is an eigenvalue of a, and x is a corresponding eigenvector, then the vectors x don't change. So even though you're taking the matrix A and then you're going to a to k, your lambdas are changing. So you won't get the same lambda. But when you have lambda eigenvalue of a and you have lambda to the k and eigenvalue of a to the k, the vectors x in the eigenspace corresponding to lambda to the k are the same as the vectors x corresponding to lambda. Okay? So we're raising lambda to the k, but we're not changing the eigenspace. Okay? So the eigenspace of a corresponding to lambda is the same as the eigenspace of a to the k corresponding to lambda to the k. Okay? The vectors don't change, just the eigenvalues change. Okay? That's theorem 5.2.3. So example 6, find a to the 13th where a is equal to 0, 0, negative 2, 1, 2, 1, 1, 0, 3. So we're going to find a to the 13th power where a is that matrix. Okay, so here's the solution. First, let's note it. First, if you do this and you find that this matrix diagonalizes A. So here's P. So that's a P that diagonalizes A. Okay, so if you have a problem like this, first find a matrix P that diagonalizes A. And so you can follow the steps earlier for diagonalizing a matrix. In step 2, we form the matrix P. You do that. So in the 3-step procedure for diagonal matrix from before, just do steps 1 and 2. At the end of 2, you have the matrix P that diagonalizes A. And so that you do that first. So you find the matrix P that diagonalizes A. Excuse me. Then, first, so if P diagonalizes A, that means that A is equal to P inverse dP for a diagonal matrix P. So I guess there's 2 ways to view it. You could either say A is equal to P inverse dP, or you could say oh no, that's fine. Okay, so if P diagonalizes A is equal to P inverse dP, but if you left multiplied by P and right multiplied by P inverse, you're going to get P inverse is equal to D. Alright, I'll do it this way. Okay, so saying P diagonalizes A, you could either say A equals P inverse dP, or you could say D is equal to P inverse AP for an invertible matrix P, right? So what would just happen is that the P you chose here, you take the inverse of it, and that would be the P here. Okay, there's 2 ways to say a matrix diagonalizes A. You could either say that A is equal to P inverse AP, or you could say, P inverse dP, or you could say D is equal to P inverse AP. Okay, and so I'm gonna, for this problem, I'm gonna have to use D is equal to P inverse AP. Okay, so for matrix A, it's diagonalizable if there's a diagonal matrix D and some invertible matrix P such that D equals P inverse AP. Again, if you have a matrix A that's diagonalizable, there exists a diagonal matrix D and an invertible matrix P such that D equals P inverse AP. Okay, and so using that, we can also say, if you do some algebra here, matrix algebra, you left multiplied by P and right multiplied by P inverse, that's equal to A. So P, D, P inverse equals A. Okay? And so the reason why I'm saying that is because A is equal to P, D, P inverse, but then raise both sides to the 13th power. So A to the 13th power is equal to P times D times P inverse to raise to the 13th power. And what that equals to is P times D times P inverse times P times D times P inverse times P times D times P inverse times P times D times P inverse, where you repeat this, where you multiply 13 of them. Okay? And so I'm actually not requiring you to multiply them 13 times. Instead, this is what happens. The P inverse and P here cancel. When you multiply a P matrix by its inverse, it becomes the identity, and it goes away in the multiplication. So P inverse P is gone. This P inverse P is gone. This P inverse matches with the next P. This P matches with the previous P inverse. So all the P inverse P's in between go away, and you're left with, this is equal to P times D. This goes away, you get another D. This goes away, you get another D. This goes away, you get another D, and you keep going, and there's a D here, D here, D here. There's 13 Ds, And then there's the P inverse at the end. And so this is equal to P times D to the 13th power times P inverse. So what we found, we were finding A to the 13th power. Well, A to the 13th power is equal to P times D to the 13th power times P inverse. Okay? And so the reason why we did this was because D to the 13th power is much easier to find. We're finding a diagonal matrix raised to the 13th power. And to find a diagonal matrix raised to a power, you just raise the entries on the diagonal to that power. So D to the 13th power would be just taking the entries on the main diagonal and raising each of them to the 13th power and then putting them in that place. Okay. And so the eigenvalues of, so here where I found P, the eigenvalue corresponding to this eigenvector was lambda equals 2. The eigenvalue corresponding to this eigenvector was lambda equals 2. And the eigenvalue corresponding to this eigenvector was lambda equals 1. So those are the eigenvalues, okay? So I found eigenbases for each eigenspace, right? The eigenvalues were 1 and 2. And so a basis for lambda equal, the eigenspace corresponding to lambda equals 2 was this vector and this vector. And the eigenbasis for the eigenspace corresponding to lambda equals 1, which is this vector, that's what I chose. And so you have two eigenvalues forming that P. And so D here, right? D here is going to be, D is going to be a 3 by 3 diagonal matrix where the entries on the main diagonal correspond to the eigenvalues whose ordering is determined by the order of the eigenvectors I chose here. So lambda equals 2, lambda equals 2, lambda equals 1. So 2, 2, 1 are the entries on the main diagonal, and everywhere else is 0. That's D. Okay? Right? The main diagonal are the entries on the diagonal, going up the top left to bottom right. And so the order is 2, 2, 1. So that's D. And then D to the 13th power is just taking each of those entries and raising them to the 13th power. So 2 to the 13th is the first diagonal entry, 2 to the 13th is the second one, and 1 to the 13th is the third one. Okay, and 2 to the 13th power is 8,192. Okay, and so this matrix is 8,192. This is 8,192, 0, 0, 0, 8,192, 0, 0, 0, and then 1 to 13 power is 1. Yeah, 8,192. Okay, so then, so that's D to the 13th power. And so then it's just P times that times P inverse. And so P is this matrix. And if you find P inverse is, so all this work I did here, that told us that this is equal to P times D to the 13th times P inverse. So I'm just going to erase this here, give myself some more room. So we have that that's equal to P times D to the 13th P inverse, and that's equal to P, which is this matrix. And so this is matrix multiplication, plain and simple. So when you get these matrices, you're just going to have to multiply these matrices to get the answer. And so D to the 13th power is that matrix. So it's 8,192, 0, 0, 0, 8,192, 0, 0, 0, 1. That's D to the 13th power. And then P inverse is the inverse of that matrix. So you have to find the inverse of a matrix. And so when you find P inverse, you get the matrix 1, 0, 2, 1, 1, 1, negative 1, 0, negative 1. And so now you found P, you have P already, you found D to the 13th power, you found P inverse, you multiply those matrices in that order, and you get the final answer of negative 8,190, 0, negative 16,382, 8,191, 8,191, no, 8,192. 8,191. 8,191. 0. 16,800. 16,383. Okay, so a lot of this is just multiplying and adding. Okay, and so this is just calculations. Okay. Yeah, so it's just calculations, and you multiply those matrices, and you get that. Okay, so it's just busy work. Okay, pencil push. So that's the answer. That's a to the 13th power, and that's the answer to example 6. John? Okay, another definition. If lambda naught is an eigenvalue of n by n matrix A, then the dimension of the eigenspace corresponding to lambda naught, then the dimension of the eigenspace corresponding to lambda naught is the geometric multiplicity of lambda naught. And the number of times lambda minus lambda naught appears as a factor of the characteristic polynomial of A is called the algebraic multiplicity of lambda naught. Lambda naught. So if lambda naught is an eigenvalue of n by n A, then the dimension of the eigenspace corresponding to lambda naught is the geometric multiplicity of lambda naught. And the number of times lambda minus lambda naught appears as a factor of the characteristic polynomial of A is the algebraic multiplicity of lambda naught. Okay, so that's the definition of geometric multiplicity of an eigenvalue and the algebraic multiplicity of an eigenvalue. And then the last thing in this section, 5.2, is Theorem 5.2.4. And that theorem says if A is a square matrix, so if A is square as a matrix, then the following two things. A, for every eigenvalue of A, of matrix capital A, so every eigen value of matrix capital A, the geometric multiplicity is less than or equal to the algebraic multiplicity. And B, A is diagonalizable if and only if the geometric multiplicity, so A is diagonalizable if and only if the geometric multiplicity of every eigenvalue is the same as is equal to the algebraic multiplicity. Okay, so in B it says A is diagonalizable if and only if the geometric multiplicity of every eigenvalue is equal to the algebraic multiplicity. Okay, so for every eigenvalue, the geometric multiplicity is less or equal to the algebraic multiplicity corresponding for that eigenvalue. So geometric multiplicity less or equal to algebraic multiplicity. So A is diagonalizable has the same truth value as a statement to the geometric and algebraic multiplicities are the same for every eigenvalue. Okay? So one is always less or equal to the other. If they're both always the same for each eigenvalue, that's equivalent to saying that your matrix is diagonalizable. And so if there's for some value, if for some eigenvalue the algebraic and geometric multiplicities are different or not the same, then that matrix A is not diagonalizable. For instance, if you have the eigenvalues lambda equals 1 and lambda equals 2 for your matrix A, and for lambda equals 1, the dimension of its corresponding eigenspace was 2, its geometric multiplicity would be 2. If you find its characteristic polynomial, I'm talking about lambda equals 2. If lambda minus 2 appears twice, exactly 2 times as a factor of the characteristic polynomial, its geometric multiplicity is 2. And so if those two are the same, and they're the same for every other eigenvalue, it's diagonalizable. So if for lambda equals 2, the basis for its eigenspace has 1 vector in it, the basis of its eigenspace was 1, if the dimension of its eigenspace was 1, then its geometric multiplicity would be 1. But if lambda minus 2 appears factor exactly twice as a factor of the characteristic polynomial, then its algebraic multiplicity would 2, and it wouldn't be equal for that eigenvalue. And right away, if there's one eigenvalue where the geometric multiplicity and algebraic multiplicity are different, then A is not diagonalizable. Okay? Okay, and so I'm going to stop there. We covered quite a bit this lesson, and so I'll finish chapter 5 and do 5.3 the next lesson. Okay, bye.